Hi there guys, welcome to this first video on differentiation. Now, what we're going to have in this is a function of x. So our normal graphs, our normal functions are y and x axes. So we might have something like this particular function. Now, you'll hear me use that word function a lot, and sometimes we can, instead of writing y equals, we could write it like this. And that also means a function of x, function using x's. It's pretty simple. Now, before we go any further, I just want to give you an insight on why we differentiate. So here is a particular bit of software that I can use to prove some things. Oops, where's it going? Sorry about that. Now, green line is this function here. It's x squared minus 3x plus 4, a quadratic. Now, you'll notice that, I'll just click off this gradient for a minute, this blue line is a tangent, and to find the gradient on a curve, we actually have to draw a tangent. Now, you'll do this in maths, but you also often do this in physics as well. So it's a pretty handy tool to know. So if I move this point around, you'll notice that this tangent is getting steeper and steeper and steeper. If we come the other way, it gets less steep. When we reach the bottom, it actually levels off. The gradient is 0 here. And this is called a turning point. You can check that out in the later videos. When we come up this side, the gradient turns to negative, and again, it gets steeper the higher I go. So you can see the gradient changes all the time. Straight line graphs, the gradient is always constant, so there's no real need to use this differentiation process, but you can. Okay, if I take it to this point, and I show the gradient, I'll just make sure I'm exactly on the point. You can see the gradient here is 3. 3 divided by 1 is 3. Now, in a later video, I'll take this and I'll prove and show you how we use differentiation to find gradients. But this first video is just a basic on all the rules, if you like. Okay, so if we have a function like this, y equals, when we differentiate, it's really simple. You take the power and you multiply it by this coefficient, that's the number in front. So 3 times 2 is 6. You repeat the base value, and this index is always going to be reduced by 1. So that's just going to be a 1, or even better, 6x. Now, what do we call it here? We're not going to write a sentence. This is this function differentiated, so we have this. We pronounce it dy by dx. Now, if it's given in this form, which at GCSE level it's not often, we can say it's this function, but it's differentiated, and we just have this little dash here. And that would be the same answer. But because we mostly get it in this form, that's what I'm going to focus on. So, let's write another one. Let's go for 9x to the 4. Now, when we ask you to do this, it's always going to be an index form. And you'll see in later videos it's not an index form, but we put it in there. So just bear that in mind. It's always going to look very, very similar to this. So power times the coefficient, so dy by dx. 9 fours 36. Base value is constant, and we reduce the power by 1. It's as simple as that. The quadratic graphs could be unhappy, and the power can be negative as well. So we say dy by dx, multiply these two, 6, reduce the power by 1, minus 4. Be really careful with your negatives. Now in a later video I'm going to show you that this is the same, but that's just the next step, okay? Don't worry about it now, it's just this isn't good enough as an answer, and I'll cover it later on. Now, it's not always just one term. We could have a more complicated graph, something like this. Now, let's just do the same thing, but we're going to do one term at a time. So 2 times 3, so I better put dy by dx. 2 times 3 is 6, reduce the power by 1, and you get the 2. I put a plus there because I know that 2 times 4 is going to be a positive. But 2 times 4 is 8, and I reduce the power by 1. Okay, so it's really easy when the power is above 2. But if, for example, I put a 5x there, please remember there's a 1. Now 5 times 1 is 5. If I reduce the power by 1, I get x to the 0. And you should know at this point, anything to the power of 0 is 1. So that's actually just 5. And if we have a constant term all on its own, technically there is an x there, but it's to the power of 0. Now if we times by 0, it all just cancels out. So if you've just got a constant term, they're pretty much disappearing. They're not going to feature at all. It's because you're multiplying it by 0 and therefore cancelling it out. So if you've understood that, here's one. It obviously looks horrendous. It's just so I can get all the examples. But try and pause the video and have a go and then hit play when you're ready. Okay, so dy by dx, 5 times 4, 20. Reduce the power by 1. 3 times negative 2, it's minus 6. Reduce the power by 1. And that's it. Just keep going. 2 times 2 is 4, so it's positive 4. Reduce the power by 1, so I'm just going to leave it like that. Okay, there's a 1. If you need to put that in there at the start, that's fine. But 1 times negative 3, that's negative 3. Reduce the power by 1, that's x to the 0, so I'm going to leave it like that. Okay, the constant term, they're going to go. Remember, the reason is it's x to the 0. 0 times anything is 0, so that's going to cancel it out. Okay, so even with a really horrific looking function, the derivative is not that bad. So I just dropped a new word there, derivative. That's what we call this. This is the derivative or the gradient function. And what this does is allows us to find the gradient at any point on a curve. So there'll be plenty of exercises for you to practice and just practice this basic skill, forming dy by dx or forming the derivative. And then when you're ready, check out the next video.